making theories for failure. Well, we start with a similar experiment like before. Remember, in the past, we had talked about Instron machine loading a specimen to failure in tension. Here we have a different specimen. This specimen is looks very similar to the earlier specimen, except that now this is going to subject to forces as shown. You have four forces acting on the specimen. If you draw the shear force diagram, which is shown first, you see that the force, this force causes increase in shear force on the left. It is constant and then goes down to zero. Then we have this region where the stress, the force is zero. This is force equal to zero, right? And then we have again force goes negative, stays constant, and goes back to zero. Now, if you want to find the bending, draw the bending moment diagram, what you do is you do the area under the curve. The area under this curve is it's the area of the rectangle. It's going to be force times A. Then this is going to vary from 0 to FA as shown here. It remains constant for majority part and again dips from FA to 0, right? Because this area is minus FA. So this is the bending moment diagram, which is shown below. Okay, so let me shade that area. Okay, so now the question is how can we use this specimen to model failure? So before we do that, let me try to understand how we can write the bending moments in a slightly different way. So what I'm going to do is write a formula for the bending moment. So remember, the bending moment is given by the pure bending equation. That's because if you see this section right here in the middle, this part, we have pure bending. In fact, it's true for this region, right? Pure bending because the shear force is zero and you have only a bending moment m. So this is a pure bending case where you can write the expression for sigma x shown here. Sigma x is my divided by I, but m we found is force times area. Sorry, F times A is the length. This is actually FA is the area, right? So then what we can do is we can assume that the force is actually a cyclic, right? Because what we're going to do is we're going to load this specimen with a cyclic load to simulate fatigue failure. So I substitute the value for F. We have F0 sine omega t. I can pull terms which are not time varying in one place, and then I end up with something times sine omega t. That something is sigma 0, that's nominal stress, which is independent of time, and then we have the sinusoid. Okay, so if you plot sigma x as a function of time, so this is sigma x as a function of time, what you see is it's basically a sinusoid. Clearly the amplitude is sigma 0, so it goes from sigma 0 to minus sigma 0, and that just keeps cycling depending on the loading. Okay, now what you can do is if you want to measure the cycles, right? Cycles means how many times are you going to cycle through a positive to a negative load. You can just start counting the number of peaks. You could either count the number of peaks, or you could just count from here. Let's just count from here. So n equals 0, n equals 1, so that completes one cycle. Then n equals 2, and so on. So this is basically saying that there are just two cycles shown, but a machine element like, say, a car on a tire on a car, which is traveling millions of miles and it is rotating all the time, it's going to have many millions of cycles. So you'll have the sinusoid appearing in machines like cars or planes or anything which is moving several million times in its life cycle. So now what we want to do is we want to model this failure, and so what we do is we follow two steps. So this plot is obtained by following a procedure with so we're going to use this idea that we have this specimen in the lab and it is subjected to this load, in fact this load, and we are going to try to arrive at this curve. So what we do is we follow the following step. First is we fix sigma 0. Okay, so if you look at sigma 0, it's basically f0 a y I. A is a, y, and I are constants for that particular specimen. So I is the inertia and y is the distance from here to the neutral axis to the peak, to the end of the specimen, and then f0 is just the load, right? So what we can do is we can fix sigma 0, we can do that, and then we will follow a procedure where we'll increase n. What is n? N is basically the cycles. You see all this, n equals 0, n equals 1, so on. So we can just keep doing this for 100 times, 200 times, 1000 times, so on, so forth. Okay, there was a question. Yes, so we are no longer on the content of the midterm. What we have here, uh, this part is going to be your final exam content. So yes, this is homework 7 and later. This is not midterm material. You're right. I just wanted to finish the midterm material so that you have enough time to do the homeworks. Yeah, so this is not on the midterm. You're right. Okay, so then we'll keep increasing n, and we do that till this specimen fails. Okay, so we'll do this till it fails, and each failure will give us one dot. So when we do this, this will go till failure. Till failure. Okay, what that has given us is going to be one single of these dots, right? That's the point where it failure occurs. So if you want to get these multiple points on this curve, and by the way, let's say that this is a certain sigma 0, and then this is the certain n, right? So we got 1 point from 1 and 2. So next we'll repeat 1 and 2 till we get multiple points. Okay, so what it means is we'll get this one, so on, so on. So we have to do this so many times, right? We do this, and what appears is this plot. Okay, this plot is known as the SN curve. Here it is, SN curve. S because we abbreviate the strength as S, and N because we indicate the cycles on the x-axis. So SN curve. So you can see that there seems to be a line which is approximately can be fit into this. So this is basically taking a non-linear regression. Regression is fitting a line. It's non-linear because there's not one straight line which explains the whole data, but it's this sort of a curve. And what we can do from this curve is we can identify there are three regions. The first region is stops over here, starts here and stops there. So this is the first region. Okay, this region is called low cycles. Okay, what is low cycles? It's any stress, any cycles which go from one cycle, 10 raised to 0 is 1, to 10 raised to 3, 1000 cycles. That's low cycles. Then we can draw another line. Well, it's a curve, but it's like this. It reaches about 10 raised to 6. So it's basically a curve, a slight curve, but it can look somewhat like a line. Okay, and we'll actually do an approximation, it's a straight line to make it easy for ourselves. And this part is defined as, well, it's not really high cycles, but there's a clear demarcation. And then from here, it's almost flat. This part is just flat. What it means is that at some strength, you'll see that the number of the cycles goes to infinity. This will just keep going, right? So we have, this is a million, 1 million, and 1 million is like a very important point on this SN curve. After 1 million cycles, you'll see that you go 10 million or 100 million or 1000 million or 1 billion, you'll see that there is no effect on strength. It doesn't really fail, to so to say. It just stays constant. So there is this critical strength at which this will occur. This means that the specimen, whichever testing, is never going to fail. It's going to just withstand any failure. So it's going to be there lifelong. This life is not an infinite life. Okay, because clearly after this point, you see that the curve is flat. Okay, so we have Low cycle, 1000. We have high cycle. Anything above 1000 is high cycle. And then we have finite life. The reason why we'll call it finite life is because all these dots indicate failure occur up to about, I mean, they appear up to 10 million, but we're going to, for all practical purposes, we'll assume that it's actually going up to 1 million. Sorry, 10 million. So you can see it ends over here, right here, 10 million. Uh, so after 10 million, it becomes sort of infinite life. So there's a boundary of where there's an overlap. So there's infinite life here, there's finite life, and you can see that there's this hazy boundary where we could say it's sort of finite life or infinite. It's questionable, but for all practical purposes, what we'll do is we assume that finite life is up to here, up to 10 raised to 6, and after 10 raised to 6 is infinite life. So we can assume that this finite life ends here, approximately here, and then here we have infinite life. Okay. So this curve is known as the SN curve, as I said, and the most important part of this curve is going to be modeling this part. This is the most critical part because when we design something for the real world, we really don't want to stop at 1000 cycles. That's just so less number of cycles. We probably want to go above 1000. We want to go in millions, right? And so the thing we are really obsessed in this course is 1000 to 10 raised to 6, and then beyond that 10 to 6 it becomes infinite. So we are more or less interested in these two parts, this part and then this part. Okay, so we'll get to that part in just a bit. So here we have taken this curve which looks non-linear, which comes from experimental data, and modeled it into three regions. First region, low cycles, next region, high cycles. But within high cycles, we have this part where it is finite life and high cycles, and infinite life, high cycles. So low cycles, finite life. Low cycles always finite life. High cycles can be finite life or infinite life. Okay, so we have these three regions. Okay, and the key thing is to being able to model this region. Now, what we're going to do is, uh, in order to fit lines to this region, what we need to do is we need to know, if you want to model a line, we need to know the locations, the xy coordinates of 2 points. So for example, this point, let me use a different color here. This point is, the x-axis is n. So this is one cycle, 10 raised to 0 is 1, right? And then the y coordinate is SUT. Okay. For this point, we can see that it is 1000, and then the y-axis is f times SUT. So what is f will be clear in just a bit. It's a fraction of SUT, clearly. F is clearly less than 1. And then we have this point. There's a different color for this. This is 10 raised to 6 for the x-axis, and SE for the y-axis. This SE is going to be very important, endurance limit. We'll come to that in just a bit. Okay, so we've got this curve, and now the important thing here is that we are really interested in modeling this line. Now it turns out something which I did not tell you is this is actually a log-log plot. Uh, this is log, and this is log. Okay, so you can write this equation of this line as y equals mx plus b. They have written it. Let me just write it the way they've written it. Okay, this is the equation. I'm just going to expand this out. S f equals a n raised to b. So if you take, so it feels weird, right? You have this equation, they've written this, but this is not equation for straight line. This is equation of a exponential. There's n raised to b. So this, what they have shown here is, seems kind of absurd. Actually, what they have shown here is, this is the equation, but it's in the log. The curve is drawn in the log-log scale, but they have written this equation without the log. So if you take the log of this, so log SF equals, you know what, I'll write it down. And I'll clear this confusion just a bit. So what they've written here, I'm going to write it down here. SF equals a n raised to b. So if you take the logs of both sides, um, log log a n raised to b, but you know that log can be written as a plus b log n, right? This is the formula for log expansion. So this, we'll call this y. That's the y-axis. In fact, this is log, as I said, log SF, and this is log n. This is some constant, it's called that c, and then this is b times log, this is x. Okay, so this is x, this is y. So y equals c plus bx. Okay, but what is y equals c plus bx? That's the equation of a line, and that's precisely what this is. This is the equation of a line. So what they have shown here is this is actually incorrect. This is actually log of SF equals log a plus b log n. Okay, so they have just written it down and then converted the logs to they've eliminated the logs, but that's the equation of that line. It cannot be what they have shown over here because that is not a straight line. Okay, anyways, that's it's not very important of what this line is. We'll ultimately model this line and then we can have to use it. We'll never have to really use this plot. Okay, so don't worry about this too much. Okay, now that we have some idea about this line, uh, let's let's do a couple of things. First of all, let's model this line. So um, okay, so we are only looking at this range. This is very important. We are only looking at the range of 10 raised to 6, 10 raised to 3 to 10 raised to 6. This is the region where we are trying to model. We've seen that the equation looks like this. They have written down here. So in this equation, the question is, how do you get A and B, right? A and B are unknowns. They are constants. So I'm going to show you how to compute A and B. Now, what I did here was I did write down the values of A and B, but the question is how do you get A and B? So it's not very hard to get A and B. I'm just going to write sort of fill in the blanks, and I will not complete the whole derivation, but I'll just give you an idea of how A and B are computed. Essentially, what you have to do is look at this equation because this is the equation which models that line. So we can write uh, log SF equals log A plus B log n. Log SF equals A plus B log n. Okay, and remember it's after all equation of a straight line in log scale. So in order to write the equation or find the constants, which are there are two constants a and b, we need two equations. How do we get two equations? We know what these lines pass through. This line passes through 1000 FSUT and 10 to 6 SE. So we substitute those two values. This passes through uh, 10 raised to 3 F S U T. So we'll substitute the value log F S U T equals A plus B log 10 raised to 3. And then we can also say that this passes through, the other point passes through is 10 raised to 6 SE. So we can say log SE equals A plus B log 10 raised to 6. Okay, so we have here equation 1, equation 2. So we can say two equations, 1, 2, and two unknowns, A and B, right? These are the unknowns. So if you have two equations and two unknowns, you can solve for those two unknowns. And when you do that, you'll end up with these equations. You'll end up with a value for A and a value for B. Okay, it involves solving these equations. Now this log was taken to be log to the base 10. Okay, this is all base 10. Everything is base 10. And you could actually do this with other base. Just that this derivation, I'd use log to the base 10. It makes it easy because you know that log 10 to the base 10, 10 raised to 6 to the base 10 is just 6. Right? This is simply equal to 6, right? And then this is simply 3. That's the property of using log to the base 10 when you have uh, exponents of 10. This is 3. So it just makes your life easy. That's why you took log to the base 10. Anyway, so this gives you these equations. I will not ask you to derive this expression, but you need to know that the formula which models the finite life is basically this. Now the question, what is endurance limit SE? I'll get to the endurance limit in just a bit. Uh, Okay, so here remember SUT, we know SUT, it is basically the ultimate strength. When you did the stress strain curve, we got SUT. What is unknown here is two things. One is F, what's F, and what is SE. Okay, so how do we get those two? Uh, First, let's see how to get F, and then I'll tell you how to get SE. So for F, if you look at this curve, uh, which is the SN curve from experiments, this is the idea as F sits right here, okay, and it is basically this point, right? How do you find that point? Well, it's an empirical test, so you use experiments to figure that out. So remember that this is the point where the it is a point at which we have 1000 cycles. So as long as you know, if you can make an experiment to figure out these points for different loads, you can basically find that point. So what they did was they plotted F. Okay, the experimental is as a function of SUT. This is SUT as a function of F. And they found that it falls under this curve. So this was empirically obtained. Now you'll see that there is something here and there's something here. So what's the difference? Well, one of them, this is KPSI. This here is in KPSI. And then this is in SI units. SI units, SUT is, I'm blanking on SUT, it's MPA, I think. This is MPA, right? So this is how you can get the value of F, provided you know SUT. But you know SUT because iron has a different SUT from aluminum and so on. That's a material property at which things just, the material is going to break. So that's one way. If you don't like plots, what they did was they took this curve and they tried to fit this curve as a function of SUT. So it turns out that the formula for F as a function of SUT is something like this. Okay. So they needed at least a quadratic equation in SUT to explain this curve. It's not a straight line. So you could use this equation to get SUT. Okay. A third way of doing this, and if you're not given anything about you're not given the plot, or if you don't want to use this fit, and you are in general, you think that it's okay to approximate, then you approximate 0.8 or 0.9. In fact, if you try to see this curve, you'll see that it starts at 0.9 and it goes up to what, 0.76 or 0.77. So you could just assume it to be between 0.8 and 0.9. Maybe you could do the calculations with 0.9, then you use 0.8, and then depending on your conditions, you could find the minimum of the two for strength and then use that. So that is being very conservative, and that's perfectly fine. Okay, so there are multiple ways we can do this. I will tell you in the exam what to use, but if you're not given that in the field, you are free to use one of those three. You want to use the most accurate way, if possible, right? Either the plot or this equation. Okay, so we still have not got endurance limit. Now, endurance limit is actually something which is obtained from experimental data. So here we have the ideal SN curve, sorry, the SN curve. Here the SE, just like this FSUT, F was obtained from experimental data. Anything on this y-axis was obtained from experimental data. Okay, it turns out that people have found that the endurance limit is actually pretty straightforward to write down. It's basically this formula. Okay, so you can see there are two formulas. This formula is for uh, FPS because it's kpsi, and this formula is in SI units. So what this formula says is if the ultimate strength is less than 200 kpsi, then just use half of SUT. If it is greater than 200 kpsi, just use 100 kpsi. And same for endurance limit of in SI units. Okay, so this is uh, everything you need to know in order to basically model and solve for the SN curve. Okay, so the great thing about this curve is that, as I said, we don't really want to be in this range because we don't want to have a specimen which is designed for 1000 cycles. We usually want to be in this range, 1000 to 10 raised to 9, right? If you're in this range, 1000 to 10 raised to 6, then it's going to fail some point of time. And then if it's 10 raised to 6 to 10 raised to 9, it's never going to fail. So for this region, for 10 raised to 6 to 10 raised to 9, you only care about one number, SE. That's it. If the strength is less than if it's greater than SE, then it's never going to fail. And uh, if it's lower than SE, then you have to look at this curve. Okay. So what we'll do is we will solve a problem so that we can understand this further. Okay. So given a 1050 HR steel estimate, rotating beam endurance limit at 10 is to 6 cycles, so that's a million cycles. The endurance strength of a polished rotating specimen corresponding to 10 is to 4 cycles to failure, and expected life of polished rotating beam specimen under completely reversed stress of 55 kpsi. Okay, so let me translate this into formulas or variables of interest. So what you're asking at 10 raised to 6, we want to know the endurance limit. Okay, endurance limit is basically SE. So what is SE? Then the endurance strength of a polished specimen corresponding to 10 raised to 4. So if you have 10 raised to 4 cycles, what is I would call it SF. Okay, because if you go back to this figure, you'll see that anything here above 10 raised to 6 is SE, and anything between SC and SUT, between any of these cycles from below 10 raised to 6, is going to be SF. SF is some general point here. So SF is unknown. And then finally, expected life of a polished specimen. So life means N when under completely reverse stress of 55 kpsi. That means that if you subject this to 55 kpsi, then what is the life? In other words, if you go to this idealized curve, if you subject it to 55, maybe it's here, what is the corresponding n? That's what you want to compute. Okay, so let's get started. Now, we want to look at 1050 HR steel, and this is a table which gives you various steels of different grades. So we are looking specifically for 1050, which is here, HR. It looks like we need to look at this particular row. Okay, it gives you some other properties which you don't care about, but you do care about number 4 and 5, which are yield strength. Well, not tensile strength. This is the yield strength. Is basically, wait, this is SY, and this actually is SUT. Okay, so you're given SUT and SY. In fact, you're given that in both units. Yeah, you're given MPa and KPSI. MPa, KPSI, MPa, KPSI. And remember, in this problem, I think we are asked this value than KPSI. So we are interested in the KPSI more than MPa because this problem is specifically in KPSI from here. Okay, so with that, let's see how we can compute. um, First question, compute endurance is 10. We need to compute SE. So N equals 10 raised to 6. SE is unknown. Okay, so what can we get? How do we compute SE? Well, we looked at this formula. SE, actually I did SE prime. SE prime is 0.5 SUT or 100. So we need SUT in order to compute SE prime. That's what it gets to. So let's see what SUT is for 1050. So we have 90 kpsi. So we'll write it down. SUT is 90 kpsi. I'll write it SE prime. From here we have, if SUT is less than 200 kpsi, then SE prime is 0.5 SUT. So that's the formula I want to use. So SE prime is 0.5 SUT. So 0.5 of 90. And this is 45 kpsi. So the answer is 45 kpsi. Okay, next question. We are asked to compute SF at 10 raised to 4. So at n equals 10 raised to 4, SF, what's SF? Okay, now remember that the SN curve, and you can just look at the idealized one, has three parts to it: low cycles, high cycle finite life, high cycle infinite life. First, to identify which region this lies in. So we are asked to compute what is the strength S at 10 raised to 4. So clearly this is high cycle finite life. That's very important. If you don't know this region, you cannot release, you may get the wrong answer. You can't use that formula we derive for any other region. So we are looking at high cycle finite life. This is high cycle finite life. So if it's high cycle finite life, then the formulas for high cycle finite life are given here. So we need to use these formulas. So we have, first of all, SF equals A times n raised to B, and then A equals F square SUT square divided by SE prime. So it's written SE, I'm going to write SE prime. And actually there's a distinction between SE and SE prime. I'll get to that in the next section. And then B is 1/3 log to the base 10 SE prime divided by F SUT. Okay, so now let's see what is known, what is unknown. Uh, we need to get A and B, and then only we can compute the other one. So this is known, N, it's 10 raised to 4. SF is unknown. A and B need to be found from these equations. In this equation, SE prime is known because it's 45 kpsi. SUT is known, it's 90, it's from that table, 90 kpsi. What's unknown is F. So we need to find F. So how do we get F? Well, we know that there are three ways to do it. We have this curve, and then we have the fit to the curve. Okay, the easiest way is probably the third one is less accurate. Probably the easiest way to do it is to use this one. So let's see if you can use this one and see what we get. So SUT is 90 kpsi. 90 is here, sitting right here. Okay, it's between 84 and 86. So you could ballpark it and say it's 0.86, or if you want to be more accurate, you can use this equation. So in this equation, what you'll do is you'll put SUT in the first equation, because this is look at the range. It's from 70 to 200 kpsi, and we are sitting at 90 kpsi. So if you use this formula, if you put SUT equals 90, you can get a more accurate value than what you would get here. So what I did was I actually used the curve fit method too. using method 2 FSUT curve with SUT equals 90 kpsi, we get F equals 0.855. 855, and you can see that's so close to what we see from just ballpark. It's about close to 0.86, right? 855 is very close. So looks like we're in the right, we have the right value. At least we verified with the curve. So that's what you get. So now we just have to sub in this value in there, in here, and then we have A and B, and then we can compute SF. So I'm just going to fill the blanks. So A comes out to be using 855 SUT square divided by SE prime 45, and then B equals 1/3 log to the base 10 S E divided by F times SUT. So A comes out to be 131.8, B comes out to be minus 0.0766, and so we can compute SF as A times n raised to B. SF is unknown. A is 131.8. We know that n is 10 raised to 4 and B is minus 0.0766. So subbing in the value, we get SF as 64.39 kpsi. Okay, so that completes part B. Part B was computing cycles to failure. Then the last one is expected life. So we need to compute n when SF is 55 kpsi. So we can use, okay, 55. Now, here's something which you need to be very careful. It's 55. Uh, so it's 55. The question is which range, which region it's going to be. Now we know that SE is 45. And we know that FSUT is what? 0.855, uh, around 0.86. So F was, let's see, F was here 0.85, 0.855 times SUT. SUT was 90. I'm just going to quickly compute 0.855 times SUT. So it's 76.95. Okay. So part C, FSUT is 0.855 times 90 is 76.95. And then we know that SE is 45. And then if you look at the curve, we have three regions. So we have this, then it's down, and then it's flat. Okay. And then we know that this part is 10 raised to 3, this part is 10 raised to 6. However, you also know that this is SE, so this is 45, and then this part is FSUT, so it's 76.95. So if you are asked to compute uh, n at SF equals 55 kpsi, we are very certain that it is going to be here, right? 55 is somewhere here. So we know that this is the part of the curve which is needed in order to explain n. So we need to look at this part. So SF equals A n raised to B. The only reason I did this is because we do not know when we start off if it is this region or it's this region. This is very clear. It's not this region because 45 kpsi is the limit on this one, and we are at 55, but we don't know if it is this or this. So that you can only find that if you know FSUT. So this is very important. If you don't do this, you will end up using the wrong equation. You need to understand if it's this equation or that equation. So here we have to use SF equals A n raised to B. So let's use that equation now. SF is 55. A is 131.8, I think. This constant doesn't change. It's the same as before. So 131.58, because the material has not changed, and so you'll have the same value. N is unknown, and B is minus 0.0776. Okay, so if you want to solve for N, what we do is we bring this down, and then we do 1 divided by minus 0.0766. Okay, so you just take the ratio. Okay, and then if you do this, if you calculate this value, you get 76,000 cycles. Or if you want to put like a better number to it, let's call it 7.6 times 10 raised to 4 cycles. Okay, and what you notice is that this N does lie between 1,000 and 1,000,000.